Hello, welcome to this video on resonance circuits. The purpose of this video is to help you with your labs. This week we have one of the experiments that talks about series and parallel resonance. So I'll be trying to address some of the theoretical aspects of that and show you how to calculate the resonance frequency, and you can as well get the cutoff frequencies and so on. So let's consider first what we call a series resonance circuit. A series resonance circuit is made of a capacitor and the inductor in series, and of course you have the source resistance. This is your source here. It's a sinusoidal source. It has an amplitude A and an angle of 0, so it's A cosine omega t, and this is your load here. Okay, and of course you can do all types of calculation in this circuit. You can find the total input impedance seen by the source from this side. So Zn, okay, in the same way we do it in DC, is going to be Rs plus the impedance of the capacitor plus the impedance of the inductor plus the impedance of the load. So it's Rs plus RL. The impedance of an inductor is J omega L. It increases its magnitude. You can see this omega here. It increases with frequency. And the impedance of a capacitor is 1 over J omega C or minus J over omega C. So this impedance decreases with frequency. So the higher the frequency of your source, the lower the magnitude of the impedance of the capacitor. Both of them have purely imaginary. They don't have a real part. Okay, and this J here simply means that there is a phase shift of 90 degrees between the current across the inductor, the current going through the inductor, and the voltage across the inductor. This is what this J means. Okay, with the voltage leading. This minus J here means that there is a phase shift between the current going through the capacitor and the voltage across the capacitor, with the current leading. Okay, so J and minus J really they have an interpretation of a 90 degrees plus or minus phase shift. Now I can take this input impedance and take J omega L as a common term. So I get here 1 minus 1 over this term here. This becomes omega squared. I have L here. Okay. Then what is the total current flowing in the circuit? The total current, as we did in DC, is the phasor of the source divided by the total input impedance. So it's A angle 0 divided by Zn. I'm assuming my source to be A cosine omega t. But when we deal with phasors, the term omega does the time domain bar doesn't show. We just say it's a cosine, its amplitude is A, and its angle is 0. So you divide this by the impedance Rs plus RL plus J omega L multiplying 1 minus 1 over omega squared LC. You'll notice something here. If you want to get the amplitude of the current, you have to take the modulus of this term. If you take the modulus, you get the modulus of the numerator divided by the modulus of the denominator. The modulus of the numerator is simply the real part squared, which is Rs plus RL squared, plus the imaginary part squared. The imaginary part is omega L multiplying 1 minus 1 over omega squared LC. So, but at one frequency, at just one frequency, 1 omega here is equal to 1 over square root LC. This term becomes 1. So this 1 will cancel with 1, and the imaginary part becomes 0. And the input impedance seen by the source is just Rs plus RL. So this frequency here, we call it the resonance frequency. It's omega naught, it's square root 1 over LC. So you can calculate that because you know L and UC. This is called the resonance frequency, a radian per second. You can get it, of course, in hertz by dividing by 2 pi. And at that specific frequency, the inductor and the capacitor cancel each other out. So J omega L will cancel minus J over omega C, and the input impedance is just Rs plus RL. So this means that the modulus of the input impedance will be minimum, which means that the modulus of the current will be maximum. Okay, so suddenly you see, if you take a look at the current flowing here, it's of course going to be sinusoidal. You see that the amplitude of this sinusoidal oscillations will peak at that frequency omega naught. Okay, let's proceed to the next slide. So as I said, if you want to get the amplitude of the current flowing in this loop, you take the amplitude of the numerator, which is A, divided by the amplitude of the modulus of the numerator divided by the modulus of the denominator. The modulus of the numerator is simply the amplitude of our signal, which is A. It can be 10 volts, 15 volts, whatever. And this is a modulus of Zn, real part squared plus imaginary part squared. Of course, at resonance, as I said, at that magical frequency in radian per second, omega naught is equal to 1 over square root LC. This term becomes 1. Okay? If this term is 1, then the whole imaginary part will cancel out. The denominator reaches its minimum value, so the current becomes maximum. We say that the circuit is going through resonance. So what's happening here? You have effectively RS and RL in series, and the inductor and the capacitor disappear. So what's happening effectively here is that there is a voltage across the capacitor, there is a voltage across the inductor, and these voltages can be big, okay? But at any instant of time, these two voltages are opposite to one another at that frequency, at that omega naught. So if you see them in the time domain, this is how things look like. One of them would look something like this. The other one looks something like this. They are exactly equal in magnitude and opposite in phase. And as a result, the net voltage that you can measure between these two terminals, which is the sum of the two voltages, will be 0. So suddenly, this LC series combination behaves like a short circuit. Okay, and this results in the current in the circuit suddenly peaking. At any other frequency other than the resonance, no, the ZL is significant. So for example, I can give you some numbers here. Maybe you can get at low frequency, you get the impedance of a capacitor, it maybe becomes something like minus 1 G1000, and the inductor say is J100. Okay, these can be significant numbers. Okay, at very high frequency, the inductor of the capacitor can be the capacitor minus J10, the inductor can be J10,000, and so on. Okay, so away from resonance, they are different from one another, but only at resonance these two impedances become equal, and as a result, their voltages cancel each other out perfectly in the time domain and in the frequency domain. Okay, so if you build this circuit here in the lab, okay, and you have the ability to tune the voltage, the frequency of your source, so this is tunable, and you keep on changing the frequency here, and you monitor the amplitude of the output voltage. Remember, the output voltage here is simply the current multiplying the resistance RL. Okay, so if the current peaks, its amplitude is becoming maximum, the output will also, its amplitude become maximum. So both are sinusoidal quantities really. The output is simply a sinusoidal quantity. But at one specific frequency, omega naught, you'll see that this becomes pretty strong. Okay, so at resonance, as I said, the amplitude of the output voltage becomes maximum, because the amplitude of the current becomes maximum. Okay, so this circuit here, at that magical frequency, you see a sudden peak in the current and sudden peak in the voltage. So this effectively acts as a band pass filter. What if we reorganize the circuit to have something like this? Okay, what is happening? This is your source resistance, and this is your LC combination. Let's take a look at this, analyze this circuit at DC, very low frequency. At DC, a capacitor represents open circuit. So this branch is open circuit. Then V output is equal to V source. You have a sinusoidal input here. It's going to be transferred to the output. What about at very high frequency? At very high frequency, because the impedance of an inductor is J omega L, so it grows with frequency. If omega is infinite, this becomes also open circuit. J omega L becomes J infinity. So this means that this branch is open circuit, and again V output and Vs are equal. What about at resonance? At resonance, these two really effectively represent short circuit. So suddenly your output voltage becomes 0. So this circuit here eliminates only one frequency. It's actually a notch filter. It allows other frequencies to go through except for the resonance frequency where it blocks it. Okay, so at resonance, this branch becomes short circuit. You get zero at the output. At very low frequency, the capacitor is open circuit because its impedance is 1 over G omega C, and of omega 0 you get minus G infinity. So this is open circuit, and V output is equal to V source. At very high frequency, say infinity, the impedance of the inductor is J omega L, so it's going to become J infinity. So again, this is open circuit, and V output is equal to V source. So let's plot the response of this circuit at different frequencies. So assume we can change the frequency, and we're going to plot the amplitude of the oscillations here at V naught. You see that at DC, you are going to get nothing. Why? Because at DC, a capacitor is open circuit. So the link is cut between the output and the input. This is open circuit. Why at very high frequency you also get zero? Very simple. Because the impedance of the inductor is J omega L. So when omega goes to infinity, J omega L becomes very large. Effectively, at very high frequency, it's open circuit. So again, the link is cut between the output and the input. And again, the output will go to zero. What about at resonance? At resonance, you get maximum current going through. Maximum, when I say maximum current, I mean the current with maximum amplitude. Okay, then the amplitude of V output will be maximum. So if you try to plot this, you see it acts like a band pass filter. It peaks only at the resonance frequency, and then it decays around that resonance frequency. If you switch the circuit to the other configuration we have seen earlier, you see an opposite behavior. You see that it's actually a band, a notch filter, or it actually stops one frequency or a band of frequencies around it. So at omega naught, suddenly you get a dip. V output goes to zero. When I say V output goes to zero, I mean the amplitude of V output will be zero, because everything here is sinusoidal. Okay, why is that? Because at resonance this is shorted, these two cancel each other out, and V output is zero. This is why you get this point here. At DC, the impedance of the capacitor is infinite because it is 1 over J omega C. So this is open circuit. So imagine that this branch is not there. V output will be V source. So V output will be maximum. At very high frequency, say at infinity, the impedance of an inductor is J omega L, so it is J infinity. So this branch is open circuit again, and V output is equal to V source. Notice when I say the impedance of the inductor is large, I say J1000. I mean it's effectively representing very high resistance to current, but this J talks about the phase shift between the voltage and the current across it. But still, it offers pretty high, what we call it, impedance. It's trying to impede the flow of current. Okay, so effectively, when this is J infinity, this branch here is open circuit. Okay, I wrote a simple MATLAB program that you can write again, take it and write again in Java or C or in MATLAB. It's written in MATLAB. If you don't have access to MATLAB, you can use another software which is pretty much identical to MATLAB, as it's free. It's called Octave. Okay, Octave you can download for free, and it follows the same syntax as MATLAB. The nice thing about MATLAB is that all operations are done in complex numbers automatically. So here I define the inductor, so I can show here the steps I did. I define the inductor, it's 10 millihenry. I define the capacitor, 1 microfarad. I define RS 5 ohm. I define RL 5 ohm. Our source is sinusoidal, it's 10 angle 0. This is just the phasor, it's 10 angle 0. This is I square root minus 1. By the way, I did not have to write that because I is internally defined in MATLAB. So I is automatically square root of minus 1. So I'm gonna calculate the impedance at 30 different frequencies. So I'm changing the impedance of my source. Frequency is K100. So the frequency will go from 100 hertz to 3000 hertz. I calculate the corresponding omega. Omega is 2 by F. ZL, the impedance of the inductor, is 1 over J omega L. the impedance of the capacitor is minus J over omega C. The total impedance seen by the source, as we explained earlier, this is simply the simple series resonance circuit. So this RS, L, and C, and this is RL here. Okay, this is a very simple one, and you have a source here. Okay, so this is RS, this is RL. This is really the circuit we are trying to program here. So I calculated the impedance of the inductor, the impedance of the capacitor. The total input impedance seen by the source is the sum of all these four terms. I sum them to get the current. The current as a complex number, everything is complex, by the way, all the operations are complex, is equal to the phasor of the voltage, which is 10 divided by this input impedance. If you want to calculate the output voltage, and this is what I need here, I'm calculating this output voltage. This is my output voltage, okay? Plus and minus, so this is the phasor of the output voltage. So the phasor of the output voltage is simply the phasor of the current multiplying RL, and this is what I have here. I'm gonna store its amplitude, so I took the absolute value, the modulus. So I store its amplitude at the kth frequency, and I store the corresponding frequency. I do this for 30 frequencies between 100 Hertz to 3000 Hertz. And then at the end, I plot on the x-axis, I have the frequencies, and the y-axis, I have the modulus of the output voltage. As we agreed, this circuit is a band-pass filter, so at one frequency, you see that your response will suddenly peak. Okay, and this is what you're expected to do in the lab. You'll be able to show this in the lab. So this is a figure I get from MATLAB. You see at the resonance frequency, I did not calculate exactly. Maybe it's about 1600 Hertz, something around 1700, something around this number. Okay, you see that the response suddenly peaks. Okay, at DC, as we agreed, you have 0. At high frequency, you get 0. Okay, of course, you can define something here called the cutoff frequency. Cutoff frequencies are the frequencies at which the response will drop to 1 over square root 2 of its top value. So here the maximum value is 5, and the way we see why it's 5, because we have two equal resistances, RS and RL. So RL gets half of the source. The source is sinusoidal with amplitude 10. Then here the output is sinusoidal with amplitude 5. Okay, so you have to determine this term, which is 5 over square root 2. If you draw this line here, which is at level 5 over square root 2, you get two different frequencies, upper frequency and lower frequency. We can determine that actually from the circuit. Simply write the expression for V output, get its modulus, and say I would like the modulus to be equal to this value here, 5 over square root 2, and then you solve for omega. Everything will be written in terms of frequency. Solve for omega. You get an upper cutoff frequency, which is this one. This is the upper cutoff frequency, and this is the lower cutoff frequency. And the difference between these two is what we call the bandwidths. This is a band that's allowed to be transmitted by this filter, and everything else is being blocked. As you see, it tries to kill all the other frequencies. It does not allow them to go through. So if your source has multiple frequencies, in our case here it has only one frequency. If it has multiple frequencies, the resonance frequency will go through without any change. Actually, you get a reduction of 1/2, because this circuit becomes like a voltage divider. At all other frequencies, you see a strong reduction in the amplitude of the output voltage. Okay, the second circuit I would like to discuss in this video is a barrier resonance circuit. The barrier resonance circuit is a circuit where we put together the capacitor and inductor in parallel. Again, the calculation follow exactly the same way. This look like one impedance and another impedance, they are in series. So this acts like a voltage divider. Then V output, the phasor of V output is equal to the phasor of the input, multiplying RL over RL plus this impedance. But what is this impedance? It is J omega L in parallel with 1 over J omega C. We follow exactly the same steps as if we have DC here. Okay, J omega will cancel with J omega. You obtain L over C in the numerator. And the denominator, I can take J omega as a common term. You obtain J omega 1 minus 1 over omega squared LC. Notice that again, you have this resonance phenomenon happening. So at omega naught, equal to 1 over square root LC. This term here becomes 1. So you get 1 minus 1. So you have 0 in the denominator. So what is Z1? Z1 becomes infinity. So looking here from this side, you see like these two behave like open circuit. The circuit looks like this. I'm going to draw it again here. It looks like this. And this is RL. So what this circuit does is that it picks that specific frequency and they try to block it from passing. Because at that frequency, these two behave really like open circuit. You can see their parallel combination becomes infinite at that frequency. Okay, so this is the opposite to the series resonance. Series resonance at resonance behaves like short circuit. Here parallel resonance behaves like open circuit. Okay, so if you have a voltage divider between RL and this Z1, at that specific frequency, the output is cut from the input. Okay, and the output, if you measure it from here, will be equal to 0. There is no connection. Okay, at all other frequencies, let's see what's happening at DC and what's happening at infinity. At DC, a capacitor represents open circuit, but the inductor is short circuit. Then the output will be equal to A angle 0. So at low frequencies, when I say DC, I mean zero frequency. When I say at low frequency, I mean frequencies close to DC. So at very low frequencies, the capacitor is effectively has very high impedance because its impedance is 1 over j omega c. 1 over j omega c. So when omega is pretty small, this number is complex but it's large, has a large magnitude. Effectively, it's open circuit. But the inductor is j omega L. So if omega is small, this becomes effectively like a short circuit. Okay? What happens at very high frequency? Very high frequency. At very high frequency, 1 over j omega c becomes very small. Effectively, if omega is infinite, if this is infinity, this becomes 0. So again, this looks like a short circuit. The inductor will behave like an open circuit because its impedance is j omega L. And if omega is infinite, then this becomes j infinity. So effectively at very high frequency, this is short circuit, and then the output will follow the input. So you could see at very low frequency, the output follows the input. At very high frequency, the output will follow the input. At resonance frequency, the output will drop to 0 because these two they represent really effectively open circuit. What is happening here is that the current going through the inductor and the current going through the capacitor, they are equal and opposite signs, so they create their own loop. And when they create their own loop, this means that the current flowing in will be 0 and current flowing out will be 0. Okay, which is really a fascinating idea if you think about it. Each one of them will store energy in one half of the cycle, and then they give it to the other in the other half of the cycle, and they keep on doing that. They create their own loop. Okay, they resonate together and they ignore the rest of the circuit, and as a result, this part becomes open circuit. Okay, let's move to the next slide. We're gonna discuss more how we do the calculations here in this case. As we agreed, this circuit is really nothing but a voltage divider. It's a complex voltage divider. So the phasor of the output, okay, is equal to the phasor of the input multiplying RL over RL plus Z1, and Z1 is the impedance of the parallel combination of the inductor and the capacitor. As we agreed at DC, V output is equal to the source. At very high frequency, V output here, if the source has an amplitude of A, so here you get A and here you get A. What about at resonance? At resonance, you're gonna get 0 because the output is cut from the input. Because Z1 is infinity. If you get here infinity, this term becomes 0. V output will be 0. So you get this sudden dip. Okay, what I'm showing here is the modulus of V output. Modulus of V output means it's the amplitude of the oscillations of V output because everything here is sinusoidal. Okay, so this circuit behaves like a notch filter. It picks one frequency and it kills the output at that frequency. While in the series resonance, it picked that frequency and allowed maximum current to go through in that frequency, at that frequency. Okay, we can change the structure of the circuit a little bit and put the impedance Z1 here. So At resonance, L and C are gonna resonate together. So at that one specific frequency, if I adjust my source to have the frequency omega naught, these two are gonna represent the open circuit. Okay, and as a result, the circuit looks something like this. Okay, you have your source, you have your RS, you have your R, and these two are open circuit. They are not there anymore. So this means that the output will follow the output which I measure here will follow the source, because there is this branch is open circuit. So at resonance, in this case, you get maximum transmission. Remember, this circuit is different from the one we had earlier. Before, the L and C was in this branch and the R was here. So when we switch the order, we convert the circuit from a notch filter or band stop filter to band pass filter. So at that specific frequency, V output will be equal to V source. What about at all other frequencies? Let's see. At very high frequency, the impedance of the capacitor is 1 over J omega C. And if omega is infinity, this term becomes J0. Okay? This becomes, sorry, minus J0. It is 0, 0. So this is short circuit. So the output will be 0. What about at very low frequency? At very low frequency, the capacitor is open circuit, because 1 over J omega C will give you minus J infinity, but the impedance of the inductor is J omega L, and if omega is 0, J omega L will be J0 or Ch0. So this is short circuit again, then the output is 0. Okay? Then at very low frequency, you get very weak output. At very high frequency, you get very weak output. Only at resonance, you get a very high output, because the output, the amplitude of the input is passed to the output, because this part represents effectively open circuit. Okay? So just remember this, how I think of this circuit. I try to ask myself at DC, what is happening at DC, and at very low frequencies, what is happening at very high frequencies. An inductor represents effectively open circuit. And okay, so at high frequency, this is open circuit, this is short circuit. At very low frequency, these ideally at DC, this is open, this is one here becomes open circuit, and this one becomes short circuit. So they alternate. At high frequency, this is open, this is short. At low frequency, this is open and this is short. So they alternate. But the result is at the very low frequencies, at very high frequencies, the transmission is is 0. V output is 0. So if you see it in the scope, you will see that the amplitude of the oscillations is 0. It should be ideally 0. Of course, if you are not exactly at DC, this not really a DC source, say it's 10 hertz, low frequency, you're gonna see something, but it's weak. Okay? So let's see how we can analyze this behavior here and write a program to handle that. One last thing I would like to show you here is is if you plot, again, this is just a plot of what I mentioned. At resonance, this part is open circuit, then the output will follow the input. So this is how you get the peak. So you get this peak at resonance. Okay? At very low frequency, the inductor is when omega 0, it's short circuit. J omega L becomes 0, so you get 0. At very high frequency, 1 over J omega C, because omega in the denominator, okay, if omega goes to infinity here, 1 over J omega C becomes 0, so the output will be 0, okay? So this is a band pass filter. This is really a band pass filter. I wrote for you again a MATLAB program. I'm gonna leave these MATLAB programs in the extra folder. You can download them, you can play with them, and I encourage you to get this package Octave, or take that same program and convert it to Java. The conversion is pretty simple, but just notice that all the calculations I'm doing here are all complex. So you have to use complex operations library from Java or C++, whatever the case it is, okay? But again, the easiest way is to download Octave. It's free, and it follows the same syntax as MATLAB, and this is written in MATLAB. If you, of course, you can have access as well to the student version of MATLAB or the professional version of MATLAB. So let's see how this code goes. This circuit is a little bit different from the one I explained earlier. So this circuit is more like the one I discussed in class. So this one here, you have RS, okay, and in the parallel branch you have RL. in parallel with L in parallel with C. But the same concept still applies. Okay, at resonance, what's gonna happen? The L and C will cancel each other out, and this part here becomes open circuit. So you have sorry, let me repeat this again. At resonance, the L and C will cancel each other out, and this part here will represent really open circuit. Okay, so at resonance, this is what you have. You have the resistance RS in series with the resistance RL, and the inductor and the capacitor are both represent open circuit. This is what you have at resonance. Okay, at any other frequency, the RS and RL will try to dampen the actually their combination will be in parallel with RL, and as a result, the net impedance will be weaker. Then the output voltage that you can measure between these two terminals will be weaker. Okay, so only at resonance you're gonna get this behavior here. One other thing to mention is about the current. When you have resonance, the current actually will go to a minimum. Why? Why would it go to a minimum? Because if the L, this combination of L and C represents open circuit, this parallel branch will have its maximum impedance, so which is RL. And if it has, because remember, when you put two impedances in parallel, the modulus of the net impedance is weaker than any one of the individual impedances, exactly like resistances. Okay, so at resonance, these two will not be there. Then the impedance of this branch will peak, and the current going through the circuit, which is V output divided by RS plus Z, this total Z will reach actually a minimum value. Okay, so this circuit really is a band, is a notch filter. It's a band stop filter. Okay, so at all other frequencies, this other than resonance, this branch will have a weaker impedance. When it has a weaker impedance, then the total Zn will be weaker in magnitude, then the current flowing will be stronger. Okay, so let's see how this file works. I defined the inductance 10 millihenry, capacitance 1 microfarad, RS 1 kilo ohm, RL 1 kilo ohm. The source is a phasor, amplitude 10 angle 0, I square root of minus 1. I repeated the calculation for 40 frequencies between 100 Hz to 4 kilohertz. I calculate the current frequency, it's K multiplied by 100. I calculate omega, it's 2 by F. When I put branches in parallel, it's better to deal with admittances, and the admittance is the inverse of the impedance. In the same way that we use the inverse of resistance as a conductance, when we have admittances in parallel, we add them. So this is what I did. The admittance of an inductor is 1 over J omega L, which is minus J over omega L. The impedance of the capacitor is 1 over J omega C, which is J omega C. I add this admittance plus this admittance plus this admittance. This admittance is 1 over R. I write here as RL, but this is a typo. It's RL. It's not RS, it's RL. But here it did not really make a difference because both of them are equal. Okay, so when you implement that, note this is a typo. This is actually a bug in the code actually, but it didn't make a difference in the calculation because they are both equal. Because here we have C in parallel with L in parallel with RL. Okay, so please change this to RL in your codes. Z parallel, once you have found the net admittance, as we do in our parallel resistances, you invert it again to get the net impedance. So the net impedance here, represented by these three branches, is the inverse of the net admittance. So Z parallel is 1 over Y parallel. Now, what is the total impedance seen by the source? It's RS plus this impedance. So this is what I have here. The current, what is the current flowing? The current is the phasor of the voltage divided by the total input impedance. So this is what I say here. The current is the phasor of the voltage divided by the total input impedance. Now I store the amplitude of the current. This is the absolute value, which is the modulus. I store its amplitude at this frequency, and I store the current frequency. I repeat for all 40 frequencies, and at the end I plot the frequencies on the x-axis and the currents on the y-axis. So if you plot it, and this plot is coming from MATLAB, this is what you're going to be getting. Again, the resonance frequency is the same one we had earlier, I know, maybe about 1600 hertz or so. And as I said, at that specific frequency, the impedance of the circuit peaks. The impedance seen by the source peaks, and the result, the current reaches a minimum. Okay, the current is gonna drop. Notice here, why is the current drops only to 5 milliamps from its maximum of 10 milliamps? Well, let's see. You have a resistance of Rs effectively in series with RL at resonance. This is 1K, this is 1K. And your source is sinusoidal, is 10 angle 0. So if you divide 10 angle 0 by 2 kilo ohm, the current going through will be 5 milliamps, and this is why at this specific frequency you get 5 milliamps. What about at DC? Why are you getting 10? Well, we are getting 10 because at DC the inductor is gonna short RL. The inductor, its impedance will be 0, is gonna short this part. So effectively at DC, this is what you have. It's just RS, and this is shorted. Okay, so this is 1K and this is 10 angle 0. So if you calculate the current here, it's going to be 10 divided by 1K, you get 10 milliamps, and this is why at DC we get 10 milliamps. What about a very high frequency? Why we seem to also get 10 milliamps? Pretty simple, because the impedance of the capacitor at very high frequency is 1 over J omega C. But if omega goes to infinity, 1 over J omega C will give you 0, which means that the capacitor is again shorting RL. So you obtain again this situation. Okay, so this circuit is really a notch filter, and by the way, you can find the cutoff frequencies here. The cutoff frequencies are by definitions are the frequencies at which the response drops to 1 over square root 2 of its peak value. So our peak value here is 10 milliamp. So I have to drop to 10 over square root 2 milliamps. Okay, so if you draw a horizontal line here at this value, I'm not sure how this value be, it's like this, and you solve for frequency, write the expression for I naught, set modulus of I naught to be equal to this value, and solve for frequency. You are gonna get two frequencies, upper cutoff frequency and lower cutoff frequency. But at these two frequencies, you can see that your response is 10 over square root 2 milliamps, which is 1 over square root 2 of the peak value. Okay, we call this one here the upper cutoff frequency, omega cutoff 1. We call this one omega cutoff 2. You can of course do the calculation in hertz or radians, doesn't matter, radian per second. And the difference between these two is what defines the bandwidth of our filter. Okay, so you're going to be doing these experiments in the lab. You're going to be playing with frequency. You're going to be observing you're doing things analytically. You're going to compare the response you're getting from the circuit with the analytical calculations. And again, it's very important to understand that a series LC combination will behave like a short circuit at resonance, while a parallel LC combination will behave like an open circuit at resonance. And we use these circuits all the time in building all types of filters for different applications.